Hello students, in this video we will see how to solve symmetric simultaneous differential equations. So here differential equations given in this form, ratios, three ratios are called as symmetrical simultaneous differential equations. So let's see how to solve them. So first method is method of grouping. So here we will try to eliminate one variable, let's say z and its derivative term dz from any two given ratios. So we will reduce this to a differential equations which contain only two ratios or two variables, and then we will solve that by using regular method. So suppose here we reduce z, okay, we eliminate z and dz terms, so we'll get something like this: dx upon some function of x and y is equal to dy upon some function of x and y. That means dy by dx is equal to, in this form, which is a first order differential equation that we can solve by using previously learned methods. Similarly, we can find second solution, and this is how we can solve this. There is one more method of multipliers. So here we are going to use this property of ratios. If a by b is equal to c by d, then that ratio is equal to alpha times a plus or minus beta times c divided by alpha times b plus or minus beta times d. So this property we will use here. What we can do here, we'll find L, M and N called as multipliers such that, okay, so here this property of two ratios we can generalize for three ratios. Okay, we'll get LDX plus MDY plus MDZ upon LP plus MQ plus NR, which is equal to all three ratios. Now we will find element such that LP plus MQ plus NR is equal to 0. This denominator term is equal to 0. This element can be constants or can be functions of x, y, z. Okay. So what happens here? We are choosing elements such that this denominator term is 0. But as we know, these ratios, okay, these ratios are exist. So if this denominator is 0 and if this numerator is not equal to 0, in that case this quantity will be not defined, it will be infinity, right? So for this quantity to be finite quantity, this numerator LDX plus MDY plus NDZ has to be 0. So this gives us this equation, LDX plus MDY plus NDZ is equal to 0, which we can solve by using either variable separable or exact differentiable form. Similarly, we can find second solution by finding another set of multipliers or by using previous method of grouping. So this is how we can solve this symmetrical simultaneous differential equation. So let us solve one example on this. So these three ratios are given and we have to find solution. So consider last two ratios. Okay, this dy upon xy plus xz is equal to dz upon xy minus xz. We can see here in these ratios we can eliminate x, so we will get ratios in terms of y and z only, like this, which gives us this differential equation, okay, which we can write as, so let us take this z dz term to left side and this minus z dy term to right hand side. Look at right hand side, this is y dz plus z dy, that is nothing but derivative of y into z. So after integration we'll get y square by 2 minus z square by 2 is equal to, so this is yz plus c1. So this is how we got first solution. But you can see here this solution does not contain x, so you have to get one more solution which contains x also. So now for second solution, let's choose multipliers x, y and z. And now see x into, so this is our p, right? So x into p plus y into q plus z into r. We can verify that this equals to 0. So we got set of multipliers such that lp plus mq plus nr is equal to 0. This implies x dx plus y dy plus z dz has to be 0. And so we got another differential equation which can be solved easily. So after solving this, we got one more solution, x square by 2 plus y square by 2 plus z square by 2 is equal to c2. So this represents another solution for this differential equation. So this is how we can solve symmetrical simultaneous differential equations. Thank you.